Assalamu alaikum guys, how are you all? I hope you are doing well and welcome to lecture 13. In this lecture we are going to study antenna arrays, the most important topic. Okay, and very interesting topic. So I hope in the previous lectures you have watched my all the videos, and I hope you really enjoy them. And today we are going to study this topic, antenna arrays. Okay, and for tomorrow and maybe we will study two topics together, millimeter wave and terahertz. Okay, because some of students are asking for to give a lecture on terahertz. Okay, so tomorrow we will study about millimeter wave and terahertz antennas. Okay. Tomorrow maybe we can change the timing of the lecture. Okay, I mean tomorrow maybe I will have a meeting with my professor, so maybe I will give lecture another time. Okay, but I will let you know before the schedule. Okay. Okay, so today we have a lecture on antenna arrays. Okay, so we will start the lecture. Okay, tomorrow yesterday I was late from my university, and today I want to finish my lecture before 2 p.m. Okay. As in the previous lectures I have discussed we have discussed that in what is the difference between the MIMO and the antenna arrays. Okay, we have antenna arrays, okay, and we have MIMO antennas. Okay, so in arrays we have a single port. Okay, as I told before, this is a patch, this is another patch. Okay, and both are connected like this. Okay, so this is array. Okay, but if you are connecting the patch with one port, okay, and another patch with another port, then this is a MIMO antenna. Okay, okay, so today we study one paper and try to design the antenna, okay, from the beginning. And some people have some questions. I mean, they even don't know how to draw and align WCS. I hope in this lecture they will understand. Okay, so this is actually antenna array, but for 5G millimeter wave devices. Okay, so in this lecture we only discuss about the antenna array, we will not discuss about the millimeter wave. Okay, tomorrow lecture we will study about the millimeter wave and the terahertz. Okay, so this is the design, and this is a wideband antenna. And you can see, first whenever you see a paper, have a look, you can see this is a design and how they have presented the paper. Okay, you see how they have used high quality figures and the graphs. Okay, so when we study about the millimeter wave, I hope I assign you topic, I mean I allow you to work on this millimeter wave antennas. Okay, and we can fabricate here and we can target. Even you see the design is simple, but the frequency is, I think what is the frequency? Okay, yes, it is from less than 40 gigahertz. Okay, these measurements are taken in Pakistan, so in Pakistan we don't have VNA more than 40 gigahertz. Okay, so they have converted the antenna, simple antenna, into antenna arrays. Okay, and there is a partial ground plane with some slots inside. Okay, and also they have fabricated the design. This looks Roger 5880 with 0.25 millimeter. So whenever you are going to design the antenna, you need to first discuss the simple antenna, single element antenna, okay, and then its parameter like S11 and sorry, design steps, okay, and then the surface current and the parametric study, okay, and then they have discussed about the simulation and measurements, okay, of the single element antenna, and then they have converted into MIMO, okay, and added the efficiency and gain graph, okay, and then they have discussed about the S11 and the radiation pattern and gain and efficiency of the antenna array, okay, and then they have discussed 2D radiation pattern or 3D, and then you have to compare with the previous research, what size they have achieved and what frequency they have achieved, what efficiency and gain etc, okay. Okay, let's start with this design first, and then we will convert into MIMO antenna array, okay. Also, if you want to repeat the lecture, I mean, if you want, you can in this paper they have converted into array, but if you want you can convert this antenna into MIMO, okay, or maybe you can create a 2 elements antenna array, okay, and then convert into MIMO, okay. Okay, yes. Walaikum assalam.
Actually, that's how it is better for us also to concentrate about how they connect the batches. You know, because this matching transmission line is very, very important.
Yes, it is important.
Yeah, if you talk about this issue before the design, if it is possible, yeah.
For the antenna, yes, we will when we start we will discuss everything, okay.
Yes.
Because when we need to convert this into antenna array, we need to check this one, okay.
Yes, it's very important issue, this part.
Yes, but the main thing is that in the antenna, when you have here 50 ohm field line, okay, and you have set the impedance at 50 ohm, and you have it is, for example, you have a lambda of this field line, and then you need to convert into lambda by 2, okay. You need to divide your field line into, they have used 4 elements antenna array, okay, and you can see here all are this one, this stub and this stub and this length and width, this length and width are of same size, okay. Okay, let's start with this one, but we will I think we do not work on millimeter wave. I mean, in this lecture we will only learn antenna array, not millimeter wave band, okay, because this one is at 38 gigahertz, okay. Okay, so we make a shape first of this kind of antenna, okay, single element antenna. In the antenna array and a simple antenna, suppose if you have designed the antenna at for example 3.5 gigahertz single element antenna, okay. Okay, sorry. Okay, suppose you have designed the single element antenna at 3.5 gigahertz, okay, gigahertz, and this give you the gain of about for example 3 dB, okay. And when you convert into this is single element, okay, single element. And in the, for example, two elements antenna array, this is your two elements antenna array, okay. And when you convert into two elements antenna, your gain will be increased more, it will become double or more, okay. It can be greater than 6 dB, okay. And when you convert into four elements antenna array, okay, it will increase more, okay, more than 10 dB, okay. So I suggest you, whenever you have mind to design antenna array, you need to go up to four elements antenna array, okay. And for the simulation results, you can discuss about the simulation results of the previous one, okay, of the single element and dual element, okay. And then your main target can be four elements antenna array, okay. Because suppose in this case your size of the antenna may be for 30 cross, for example 30 millimeter square, okay. In this case maybe your size may increase, okay, and then increase more, okay. Mostly we design antenna arrays at millimeter waveband, okay, because if you talk about the single element antenna, for example your frequency is 28 gigahertz. At this frequency your size of the antenna is very small, okay. So that's why you claim that you are shifting your design, I mean the patch, into array, okay. So that the size of the antenna increase and also the gain of the antenna increase more, okay. And you can easily fabricate the size in, because in this case what is the size of the antenna they have used? A B 9 cross 11, okay. Yes, it is fabricatable, but the size I am talking about, the size less than 5 cross 5 millimeter square, okay. So when the size of the antenna is less than 5 cross 5, because some of my designs is of size 4 cross 3 millimeter square, okay. So that is very small size. Okay, let's start with the substrate first, okay. We have a substrate, and we can use for also antenna array, if you are going to design a millimeter wave, then you can use Roger 5880, okay. Because you can also add the bending analysis of the antenna, okay. I am taking the length thickness 0.508, okay. Roger 5880. Okay, this is the substrate, okay. And we need radiator and the ground plane, okay, like this. Okay, let's create the field line first. I'm going to change the color. Okay, you can see when you click on the align WCS, you can shift your WCS wherever you want, okay. If you want in the middle, just double click on it, okay. If you want at the edges, you can double click on it, okay. And if you want at some corner, maybe you can select this one, okay, like this. And if you want this is the middle, and you want at this point, okay, so you can click on this one, transform WCS, and you can shift it at this point, okay, like this, okay. In this way you can shift your WCS. Okay, so we are going to design the field line, okay. We have a field line here. What is the width of the field line and what is the length of the field line, okay. 0.035. I am using copper here. Okay, this is a field line. Okay, but we need more longer field line. Okay, okay, this is the field line, and the shape we want to we are going to create a shape like this. Okay, it is very simple. Okay, you can align your WCS at anywhere you want. Okay, you need to create a patch. Okay, of square shape. Okay, square shape patch. Okay, and for example, you are taking 10. Let's check with this one. It is bigger. Okay, okay, this is your patch. Okay, TP. Okay, you remember the size, it is minus 5 cross 5. Okay, so here you need to take you can take 4 cross 8, I mean 8 by 2. Okay, like this. Okay, if you want more less, then you can do like this, 7 by 2. Okay, okay, my sorry, TP. Okay, so you see this is your patch. Okay, and you can cut this patch. Okay, cut this patch, the shorter patch. Okay, like this. Now you need to rotate this patch. Okay, I am going to rotate this patch. Okay, I have rotated this patch. Okay, like this. Okay, shift up little bit. Okay, now I am going to create a copy of its multi times. Okay, click copy, and like this, apply. Okay, and even in this way you can create more shapes like this. You have selected this one, you can even shift on this side. Okay, suppose if I click OK, in this way you can modify the shape, but it is looking somewhat different. But you can, if you add this one, but not I'm not going to add this one because it may take more time. Okay, so this is our patch. Okay, let's remove this one. Okay, we have this patch. Okay, we have created the patch. Now we are going to create the ground plane. Okay, half ground plane. The width same as the substrate. Okay, and the length of the substrate by 2. Okay, we are not taking full length of the substrate. Okay, and also if you want to vary the values of the ground plane, then you can add here, for example, minus b. Okay, and you click OK, and you can assign the value of b. Okay, and you see this, you in this way, if you want to change vary this ground plane, you can change the value of the b. Okay, TP. Okay, like this. If I have b, okay, I click 2, then if I click F7, and you see in this way you can vary the ground plane. Okay, now you move your WCS at this point to cut from this point. Okay, this is a slot. Okay, slot s by 2. Okay, okay, what is the slot width? I can take 2. Okay, and in the downward direction, suppose 2. Okay, I click minus tp. Okay, like this. Okay, let's increase the size of the slot. I click 4. Okay, now I select ground plane, click minus button of the keyboard, and then select the slot and press enter. Okay, we have a slot like this. Okay, now let's simulate this one. Okay, and you need to check the results. You need to check at which frequency band it is shifting, but first let me save this one file. Okay, this is a simple antenna. Okay, and for the antenna array we need to why it is close. I saved the file, but why it is turned off? Sometimes it happens with this CST. It
Assalamu alaikum, Mr. Sarraj.
Walaikum assalam.
Mr. Ahmed, did you understand me yesterday for my questions?
I did not. Can you repeat your questions? I did. I reply your questions or not?
Yes, you reply me, but you don't understand me. My confusion about the number of my antenna.
Okay.
I mean the first number and the second number, 2 by 1.
Mm-hmm.
Can you what's mean by 2 by 1 and 2 by 2?
What I need to pass you? The CST file.
I mean the first number refer for what and the second number refer for what?
You want to learn how to convert 2 by, I mean make MIMO of 2 by 2 and 2 by 1, and you are asking about it.
Exactly, yes.
Okay, yesterday we did talk on it. I mean I told you we have a suppose this a patch. Okay, I mean substrate, and if you want to make a 2 by 1 antenna array, sorry, MIMO, then for this one this is square shaped substrate. Okay, but for the 2 by 1 you need to take like this. Okay, like this is your antenna. Okay, and on the other side you can take in this way. Okay, if you want you can take like this.
It is similar to the matrix definition. It is something like matrix definitions, something like the row and the column, something like this.
Yes, and also if you want you can take like this if you want MIMO. Okay, simple MIMO, or if you want, there are many ways to make MIMO. Like if you want you can also take like this.
2 by 1 means two element. And what's mean by 1?
What?
The definition 2 by 1. The number 1 refer for what?
2 by 1. You mean like this?
It is a row. Yes. Row, I think.
In most of, yes, in the cases we talk the first one is the row. Okay, and in this case we talk about the column, but this is wrong concept in my antenna. Okay, because when I made the antenna like this. Okay, suppose like this, okay, at first I think like this, but once I Once I published the paper, then I realized that this is the wrong concept in MIMO antenna. Okay, you do not apply this one. Okay, because this is only in mathematics, but not in MIMO case. Okay, it means, what does it mean? Okay, let me explain. Suppose this is your antenna, you cannot call it 2 by 2 MIMO. Okay, a 2 by 2 means two elements of the antenna are transmitting, okay, and other two elements are receiving. Okay, so here in this case you have four antenna elements, so it means four elements are transmitting and four elements are receiving. So this is a 4 by 4 MIMO. Okay, this is a quad port MIMO. Okay, this is not a concept like we have two rows and two columns, not like this. Okay, it means if you have 2 by 2, it means two antenna elements are transmitting and two elements are receiving. Okay,
So this design is 4 by 4.
Yes, this one is 4 by 4. Okay, this one,
What's 2 by 2?
and this one is 2 by 2. Okay, because
Excuse me,
yes.
excuse me, Sir Sarosh. I want to ask about how to know or how to simulate the receiver antenna and the CST. How to get the result for the receiving antenna, not the transmitting. Because everything is
Yes.
Is the doing here and on the transmitting antenna.
When you simulate your antenna, I mean the MIMO antenna, you know, you will get many results like S11, S21, S12 and S22. Okay, the first two, I mean the first S11 and the S22 are behaving like your transmitting and behaving like a reflecting antenna. Okay, like a receiving antenna. Okay, for the other S12 and S21 are behaving like transmitting antennas. Okay, so your antenna work as both, if you have this antenna, okay, like 2 by 2 antenna, both antenna are working as a transmitter and both work are as a receivers. Okay, because you know S12 means how much effect of the other, it is also called a coupling method, but in other case you also call S21 as a transmission. Okay,
also I want to ask how much the power. I ask about the power signal, receive signal. What's the minimum power receive signal to receive the antenna? How can I check in the CST? This is my main, so I have main idea about that.
In CST, I'm not sure. I think yes, I think in this way maybe you are, if you want to calculate the power loss, maybe you are asking about power loss, and maybe you are asking about power flow. Okay, if you click on this, if you simulate the file, then maybe you will get results here. But in most of the cases, you can calculate. I mean, you have equations. Okay, I think I sent you the paper in that question. I will send you. Okay, I think I did not send you. Okay, the equations you will calculate with MATLAB code. Okay, you can export the S11 and S2 files. Okay, I mean S parameter files, and then you need to import, and then you can easily calculate the power. Okay, radiated power. And also I think yes, in CST you can also calculate in the result template maybe.
Also can get
This one.
the threshold voltage, can receive it, or the threshold for the receiving signal. Like, do you know, sometimes there's masking about some signals because the antenna is working as the filters, but sometimes need to know the threshold to receive it, the signal.
In this case, for the reconfigurable antenna, when we use the pin diodes, okay, when then we can know the voltage and other things. Okay, but for the single MIMO, I mean single antennas, I think I have seen one option, but I forgot where is this one. There is an option here, threshold. I think voltage, and I don't know where is this one. You need to find from here. Okay. Someone yesterday asked me group delay, so in this way you can calculate the group delay. Okay, oh, I will check and I will send you on WhatsApp. Okay, because here I need to find, and it is taking time. Okay, today lecture is about antenna arrays. Okay.
Thank you very much.
Sometime a CST file immediately turned off. I don't know why. I need to design again. Okay, I am going to design directly the single I mean antenna array. Okay, for this single element antenna you already know. For the antenna arrays, we have many options. Okay, we have many techniques that we apply. Okay, wait a minute.
Mr. Sarosh, I want to ask, after the simulated one element of the antenna, there are some options in the result. One of the options, I think in the plotting, I don't know where, I didn't remember, because some option you can get the one element behavior as the element. Sorry, behavior as the array antenna, behavior as antenna arrays. There are some options there. Can I use it instead of drawing many antenna?
In CST you are talking about uh,
Yes, in CST. About after the simulated one element, there are some option, one of button that called, I think, array antenna. You can get the one element behavior as the array antennas. This is the result.
yes, I think yes, there is option in CST. After simulating you will find in the far field I think option you will find a simulate array like this. Okay, we will check it. Okay, I did not use that one before, but I know there is option. We will we will check. Okay, once we simulate this file. Okay. Okay, for the antenna arrays we have many techniques because nowadays I told you people are doing research in the new types of the antenna arrays. Okay, a lot of research has been done on the antenna arrays. Okay, some people like to design the single antenna array in this way, like they have a field line here. Okay, they have a field line here and they have a patch here. Okay, and they extend this field line again. Okay, they do not divide their field line. Okay, and then connect another patch here. Okay, okay, and then again in this way they create a multi elements of the antenna. Okay, and then make array of the antenna. There are many techniques. Okay, that you can apply. Okay, let me share some of techniques that I have seen in the papers, how they have divided and used the antenna array. Okay, this is one technique. They have used port here. Okay, excited the antenna from here. Okay, they have a field line here and they have just repeat this step. Okay, this part into multi antennas. Okay, like this one. This is patch 1, this is patch 2, 3 and 4 and 5. Okay, and in this way you can also increase the gain of the antenna or make it a directional radiation pattern. Okay, for the other technique I have seen in one paper, you can also like this is your substrate. Okay, this is your substrate. Okay, and you have a port here. Okay, I mean the field line here. Okay, and you are dividing suppose this is of 50 ohm. Okay, 50 ohm. Okay, and you are again if you want to make a dual element antenna array, okay, you need to suppose this the length of this field line is suppose 10 millimeter. Okay, so for the two elements antenna you need to divide, I mean if you are using first the horizontal, sorry, okay, okay, so you need to divide your field line in this case, okay, lambda by 2. Okay, your field line is dividing into two parts. Okay, and you can say you need to take here lambda by 2 value of the field line. Okay, and then again you can take here the field line. Okay, and you can use patch here. Okay, this is another technique of the antenna array. Okay, but in the previous research they have failed the lambda by 2 concept. Okay, because in one paper I have seen that they have designed the antenna array like this is the substrate. Okay, and they have used a field line here. Okay, they have used the field line here, and they have used antenna array in a circular pattern. Okay, like this is the field line, and they have used a ring here. Okay, like this. Okay, they have used a ring like this. Okay, and they have connected the field line, small field line here, small field line here. Okay, small field line here and here. Okay, and then they have connected the patch here. Okay, in this way I saw one paper that was the circularly polarized antenna array. Okay, in this way they have designed the antenna. Okay, because in this case your concept is the previous concept, lambda by 2 concept is wrong now. Okay, in the research people just apply different techniques how they can make a new thing. Okay, that has not been done before. Okay, if you are able to make any new one, then you can also be able to publish one. Okay, like this one also there is another technique. If you want to make a multi antennas, okay, you need to use a field line. Okay, the length of the near to the length of the substrate. Okay, and then you can create uh, strip lines here. Okay, and also here. Okay, and this line is of 50 ohm. Okay, this field line. Okay, and then you can again use here like this a tree shape. Okay, you can use a tree shape technique. Okay, and they have connected the patch like this. Okay, in this way you can increase the number of the elements. Okay, and you can get the higher gain and efficiency. Okay, but it is more suggestible if you use the full ground plane behind the substrate. Okay, if you use a CPW technique here, you will not get much higher gain and will not get directional radiation pattern. Okay, so it is better if you use the full ground plane. Okay, or partial ground plane behind the substrate of the antenna. Okay, also I have seen one paper they have used like this, they have used a new technique, like they have created a field line from this point. Okay, and then they have used like this. Okay, they use the shorting pin at this point, and on the other side of the substrate they have again connected the number of elements. Okay, in a flower shape. Okay, let me use another color. Suppose this is on the other side of the substrate. Okay, they use a flower shape array, okay, on the other side of the antenna. Okay, like this I have seen in one paper they have used technique like this. Okay, so there are multi techniques people are going to apply to make the MIMO make the antenna array. Okay, but just keep in mind, if you are going to design the antenna arrays, you need to first increase your gain. Okay, increase the gain, uh, uh, increase gain as compared to the previous research. Okay, your gain must be comparable with the previous research. Okay, and it has high efficiency. Okay, if you are targeting millimeter wave band, okay, or antenna array, then it should be greater than 8 dB. Okay, gain, and efficiency more than 85%. Okay, and your main field line, main field line, I mean main field line mean this one. Okay, must be of 50 ohm. Okay, 50 ohm, because in the research you can say how you are connecting this array. You are not following any technique, you are not following any mathematics here. Okay, you are just applying a new technique to make the antenna array and to achieve the higher gain. Okay, so if you are able to achieve the high gain, but keep in mind all the antenna elements must be of the same size. Okay, like this one, and all these antenna elements are of the same size. Okay, this one and this one. Okay, so that you will not have any mismatch in the impedance. Okay, whatever the impedance is divided, like if you are using here 50 ohm, and then here you will find 75 ohm, or like this. Okay, but if you, I suggest you, if you use because you can, if you use in CST, I told you, if you want to, sorry, I did not use port here. I told you, when you use the setup solver and you click on the one option, normalize to 50 ohm. Okay, in that case you are only normalizing, or only you are uh, assigning port of 50 ohm to this point. Okay, but at these points, I mean this patch will not get the required impedance. Okay, so in that case, in antenna array, I prefer you, if you use the if you use set the impedance by yourself. Okay, like I mean by this one, by macros. Okay, you can calculate the line impedance. Okay, in this case. Okay, so in this case you need to check the impedance, calculate the impedance, and try to set with this one. Okay, not with the setup solver. Okay, and in this case your antenna arrays will have the impedance. Okay, required impedance, I mean. So in this case, if you see, there is a question. In CST, I'm not sure. I think let me create a simple antenna array here. Then we check how we can calculate the impedance of the each antenna element. Okay,
I think by mathematics, just.
yes, just a mathematics, because this is a normal case. I mean, whenever you study any
I tried before many times, but I didn't get.
in CST, there is no option of the to check the individually the impedance. You can only check the impedance of this one. Okay, or the whole antenna, but cannot find this one. But with mathematics, they did not, I think, add mathematics here. They did not add.
I want to ask you about in which paper they said using lambda over 2 is wrong.
No, I did not say. I mean, but I am saying in this case, yes, because.
Yeah, this case, okay, but all the microwave, the Bowser book and all this book, we grow up in this book, I think.
Yes, books are correct. I did not say any. I did not say that books are wrong. I mean, in the research, people are not following any mathematics, and but they just try to make any different technique, okay, and
Yeah,
achieve make antenna arrays. That's why I told you that they are not following
yeah,
any books and rules.
yeah, yeah. Thank you.
So in this case, we can, if they are not flowing, we can also make any. I don't know why this cannot be removed.
Mr. Ahmed, how to get the proper
What?
or the good length of the feed line for each patch?
Good legs, you mean?
Exactly, yes.
Okay. Okay, I prefer you, if you are flowing this field line, okay, then you need to follow this. You need to follow. Wait a minute. Okay, you have a field line, this one, okay, and you know the length and width of this field line, and whenever you try to design this one, you need to consider the length and width of this field line, okay, like if you want to design this stub, then you can divide this one, the width of, suppose it has a width of 2 millimeter, okay, and you here you can divide your like this one is w, suppose f1, that is equal to wf by 2, okay. Okay, so this is suppose your lambda, okay, not lambda but wfi, I mean. Okay, in this case, if you consider this the length and width of this field line, then you will achieve more better results, instead of if you are designing or keeping the width and length of this field line by yourself, okay. I suggest you to take this one, okay. If you want its length, then take lambda by 2 of this field line, okay. If you want width, and then you can take lambda by 2 of this width of this field line, okay. So in that case you will get much better results, okay. But if you try to, like, if it has a 2 millimeter and you are changing or varying your values here, maybe you will get mismatch in the results and also in the length, okay. Maybe you will not get much desired results. So I suggest you to follow the length and width of this main field line of the antenna, okay. Like I am.
And for the impedance, so the first feed line of it must be 15 ohms, and the second 100.
In yes, in some of the papers, if you study, I have seen some papers, they even
So it's like is a quarter wavelength.
yes, you can say, but not exactly the 100 ohm, okay. Because it can be 75 ohm, it can be 70 ohm, okay, it can be 100 ohm, but the main one, I think this one is the of 50 ohm, okay. There is some calculation, I don't know the formula here in this paper, but I will find some paper there in which they have used some calculations to calculate
Z1
the
and
impedance.
Z0 equal the impedance by 4, or I think like that.
I will download some papers on which they have because they have used they don't not design like this, okay. They only talk about the impedance of the antenna array, okay. I will send the paper.
If you calculated the equivalent impedance will become 50. That must be. This is our target.
Yes, it must be our target, or to set at 50
For the
ohm.
maximum power transfer, yeah, for the maximum power transfer is our target, because it's 100 and 100 divided by 2 will become 50.
Yes.
You know, 50 by 50 will become 50, and it will be matched with this 50 for the feed line. I think this maybe this theory is written in many microwave books.
Yes.
Yes.
Yes, it is better for if we study the books to understand the main concept, because in the research paper you will not find the exact theory, you will find only results and other things.
Yes, but we translated this 100 into the length and the width. Similar ways like we when working for the filter.
Mr. Sarush and Mr. Muhammad, I want if you used the Chibichov technique to get the transmission line matching, is more better for this, get more result, better for this result. Chibichov techniques for 3 order.
Actually, we need to try it.
Yes, you must get, because it's from 15 to 100 is more than the power losses. Do you know it? Because there is no the intermediate transition value between 50 and 100.
Mm-hmm.
So must be started to 50 if you want. It's depending it's depending the resistance of the antenna. If the resistance of the antenna is more than 50, we must graduate it from the 50 to the resistance of the antenna. If the resistance antenna is less than the transmission line, we must to reduce it. So this is the way for the Chebyshev and the binomial theory.
I will collect some papers, I mean the PDF files. Okay, I will send you to check and see how they have applied different technique. Okay, because in antenna arrays a lot of designs have been done in this shape and also in this way. Okay, but now people are trying to apply new technique. Okay, like this one. Okay, and this one. Okay, this is a new technique. They did nobody applied this one before, but now this is published one. Okay, I saw in some papers. Okay, so we can also find a new technique in antenna arrays. Okay, but I prefer if you go when you go to the millimeter wave band, then you can work on this one. Okay, this antenna array, or if you work on the multi-band antenna, like for the paper I have showed you, millimeter wave band. Okay, this one, like you have a dual band or multi-band, this one. Okay, it can also be converted into MIMO antenna. Oh, sorry, in antenna array. Okay, and to achieve this tri-band antenna, maybe it will get more higher gain and more good S11. Okay,
Mr. Farosh, what about if I use a fractal antenna in the design for the batch? Fractal technique.
we can try, because these are the techniques very less researchers has applied. Okay, if they are working on the antenna array. Okay, my main work is not on antenna arrays, but I did work on the antenna arrays. Okay, I show you some thesis. Which is this one. This is a simple antenna element. Okay, this is a simple antenna element. Okay, and this is it has a size of length 6.25 millimeter and the width of 5.44 millimeter. Okay, and this is a dual band antenna. You can see here it is operating at 28 and 38 gigahertz. Okay, millimeter wave band. Okay, and the size you know already know, and the gain is up to 7.22 dBi. Okay, and it shows a broad-sided directional radiation pattern. Okay, and there is a variation, I mean to check the change in the results. The values of the field line, the length of the field line is varied. Okay, and you see there is no big any difference in the but there is a very minor change. Okay, 0.6, 0.7, 0.75. Okay, and then the this width of this field line.
Ahmed, please, sorry for interrupting. Here for the first field line, how to get the value of the length for the first field line?
This one you mean? This one?
No, for the 15 ohms, the first.
This one?
Yes.
Okay. For this one, yes, you have.
I want to know the length. How to get the length?
Actually, you can calculate the impedance here. Okay, calculate impedance, and then according to this one, you can calculate the width of this field line. Okay, which one is the strip line? Not this one. This one, I think, or thin. Yes. Okay. Suppose here you can calculate this one. Okay, I am using FR4 substrate. I know the value of the value of the FR4. Okay, I am using 4.3. Okay, and what is the height of the substrate? I am using here 1.6 millimeter. Okay, and what is the width? If I okay, I calculate. If you take at 2 millimeter, it is not 2 ohm. Okay, I mean sorry, at 2 millimeter it is not 50 ohm. Okay, so you need to check and vary the values. Okay, in this way you can calculate the width of this field line. Okay, okay, in this way you can even it will not affect the frequency. Let me check. Yes, frequency does not affect, but the height, if you know the height of
on the phase shift is effect on the phase shift.
for the phase shift, I don't know. I mean,
change the frequency is effect.
it should not be affect the phase shift. I hope so.
Let's change the frequency and you get the phase shift is changing.
Yes, because you know at the size of the antenna is you know depends on the frequency. Okay, according to the frequency you have to take the length and width of the substrate. Okay, but here you are taking the length sorry, the width of the field line. Okay, not of the substrate. Okay,
Yes, but I need to know the length of the feed line. How to get?
for
I put randomly.
Actually, Brother Sarosh, you know, AWR, we have, I think there is a tool. I get used to use it. They give you the length of the transmission line. But if you change a little bit, it has no effect about the matching.
yes, because the main thing is this one, because your port is here, your port is here, and surely yes, this one will have a major contribution in your because it your port your impedance depends on the width of the field line, not of the length. Okay,
Mr. Ahmed and Muhammad, I want to know the limit. How to put the value of the length, the limit of the length. Excuse me, I think is we can't get the length lambda over 2. The L over 2.
Yes, by default, yes, we use it, yeah.
But in this design, previous design is not, I don't think it is lambda by 2. It's very small length.
Which design? In the paper?
No, it's opened by Ahmed.
I'm sorry, because I have some work with the student and I go under detail. Excuse me.
yes, I am talking about this design. Okay, here you can see this is your field line. Okay, this one is your field line, and they are you just connecting these small patches. Okay, like this. Okay, so I am going to design this one. Okay, you see this is the field line. Okay, this is the length. Okay, and this is the width here. So width of the field line depends on the impedance. Okay, but not length of the antenna array. In antenna array, if you see, you are connecting the elements here. Okay, you are starting to connect antenna elements here, but mainly it will consider the length of the field line from this point to this point. Okay, if I add here, they are not added, so points cannot be picked up. Okay,
Mr. Ahmed, can you please return to Chinese thesis?
yes.
Here, the first length and the second length. How would I get the length
Okay,
of feed line?
yes, here are you checking? I am varying the values of the field line, width of the field line and length of the field line, to check what is the length and change in the length, I mean shift in the frequency band. Okay, if you see, if you vary the value of this field line, you will change in the shift of the band. Okay, frequency band. Okay, so it means what we will get knowledge here. This is the field line. Okay, this is WF, and the WF is it directly not, if you see, it is when it is less, and when we moved it to up to 0.5 millimeter, and what will happen with your frequency? Your frequency at this band is shifting towards to the higher frequency band. Okay, but in this point it is shifting to the lower frequency band.
Mr. Ahmed, I don't talk about the
Yes, I know you are not talking about this one, you are talking about the length, this one. Yes.
Yes.
Okay,
Of the first and the second length.
yes, you are talking about the length of this field line and the length of this one.
Exactly.
It is given by equation, but I don't remember now.
Yes,
Equation.
yes, this is the microstrip patch antenna. Okay, and there are some equations for this one. Okay, you need to download old papers, because these are very simple design, and in the old papers they have used equations to calculate this one.
So it's not lambda by 4 or lambda by 2?
It is the small one. I think the upper one is lambda by 4, as I remember.
No,
The first one is lambda by 2.
Quarter, I think it is a quarter stable, maybe quarter wavelength, something like this, as I remember. I used it once before.
this one is, I think, lambda by 2. Okay, and the other one is lambda by 4. This one, because lambda by 4 we will have less size, more shorter size.
And I made before, I made the offset.
Okay, this design is, you can see, optimization is being done for each step. Okay, like for vertical slot and the horizontal slots. Okay, you will change the shift in the frequency band. Okay, and also the horizontal slot. Okay, you will see here, and the also bending analysis is also taken into consideration. Okay, and this design is converted into dual element. Okay, this is the bending analysis along x-axis. Okay,
Could you send us this thesis?
not sorry, because actually I have written these thesis, but they are these are not mine.
I'm sorry, because I go to underwritten with myself. I don't know from the beginning. It is your thesis?
Not my thesis. I have written my thesis for my you can say for my customer. Okay.
This is Chinese one, yeah?
Yes, I have written these thesis in brief detail. Okay, so in this thesis I have used, you can see,
Yeah.
this is a dual element antenna array. Okay, this is your radiating elements, this is your field line, this is your substrate, and this is the full ground plane. Okay, once this once this thesis will be published and accepted, I can share with you. Okay,
Okay, thank you.
because these are not my own thesis, that's why I am just telling you. Okay, because I did work on the antenna array to show you how I did work on it. Okay, I use the full ground plane in that case. Okay, this is the full ground plane behind the antenna, and this one you can see here, this is your microstrip patch. You see, I started with the single element antenna. Okay, to make it dual band. Okay, this one, this is a vertical slot and there is a horizontal slot. Okay, horizontal slot make contribution at 38 gigahertz. Okay, and the vertical slots works for the 28 gigahertz. Okay, so whenever you design, you need to start with the single element antenna, okay, and to check at which frequency your antenna is working, and then you can convert when you are converting your antenna into array.
I think in this is you already use the equation. I think to calculating the lenses.
Yes, I did not add the equations here, but I use equations to calculate the line impedance and other things, okay, and length and width of this one, okay, because it is very carefully taken into consideration. If I change the results, you see in the upper optimization results, results change a lot if you do not take these values, okay.
Yes.
So field line.
So Mr. Ahmed, the first frequency that you design, what is 38 or 28?
The 28 and 38, okay. Oh, sorry.
I mean before to put the slots.
Before I think I have added the design steps. Let me check.
I mean how to get the position of the slots.
Actually, it depends on you. You have to simulate an antenna multi times, okay. It does not as I told you, first you need to check the surface current. If your yes, you see this surface current. Let me show the surface current. Where is the surface current? This one, okay. You notice your antenna has a role, major role in these sides, okay, in these sides. So that's why I have added these loads at this position, okay.
Is this frequency at 58 or current surface?
This one is 28, okay. This one is for 28 and the lower one is for 38, okay. So you need to check the surface current, and you need to check the at which I mean portion of the antenna it is very red portion, okay. If you notice the red portion, then if you create slot at this point, at that point, I mean red portion, then you will change notice the change in the frequency, okay. And then you need to optimize the value of the slots. You can see here this is the length and this is the width, okay. So you need to optimize at because I did not exactly written the value of these slots, okay. I have optimized these slots a lot of time, okay, to set the frequency band. Like I want at 28, then surely it will work at 28. You see this is perfectly resonating at 28 and 38. This is the perfect matching.
It's amazing.
Yes.
Actually, the solution we use after we decide the place of the trapping for trapping maybe the current. Actually, we have equation. We try to use it also for the case of the not like similar to the notch band. We try to use this equation. Yeah.
Yes. Did you take the lecture of the Mr. Ihab? In his lecture, I think he exported the Gerber files and then imported into AWR, and then I think not in AWR, I think in ADS. Yes, in ADS. He used to design an antenna array in ADS software.
Yes.
So in CST, you can also design. You need to calculate the length and width of this one, okay, to check the line impedance and the perfect matching for your S11, okay. I did work a lot on this thesis, okay. This is the two element antenna, and you can see my gain is also increased. This is the design steps, you can say, okay. What happen if I this is a simple patch, okay. When I simulate it, then I see my frequency is at 26 gigahertz, okay, not at 28 gigahertz, okay, and also no frequency at 38 gigahertz, okay. So what I do, I used, when I use these slots, horizontal slots, I noticed that my frequency is shifted, okay. You can see here, okay, no, but not exactly at 28 gigahertz. So it means if I reduce the size of these slots, my frequency may be at 28 gigahertz, okay, because I taken first the most I mean wide length width of the slot, okay. Then I added the then I only check with the vertical slot, okay. I noticed that there is no change in the frequency. You notice in this case your antenna also only resonating at 28 gigahertz, 6 gigahertz, okay, not at 28 and 38. But if I added the vertical slots, I noticed that there is no change in this frequency, but you see in this band, a higher band, is now shifting towards this one. Okay, so I need at 38 gigahertz. Okay, did you understand what I mean? You need to check with the slots. Okay, first I check with the horizontal slot. I noticed that with the horizontal slot it is moving my band from left to right, the lower band. Okay, and for the vertical slot it does not change my lower band, but it is shifting my high frequency band. Okay, and then
Is put new frequency.
yes, with that slots. Okay, and also I noticed that what will happen if I keep the first patch simple and the other one with the slot. Okay, and I noticed this one. Okay, this change, and then I propose the final design. Okay, with slots. Okay, and you see this is perfect matching at 28 gigahertz and 38 gigahertz. Okay, and also the gain of the antenna is increased a lot. Okay, I have added this. Also bending analysis are taken into consideration. This is along y-axis. Okay, you see the results are almost stable. Okay, this is because the band is covering the required frequency band. Okay, 28 gigahertz, and also here. Okay, at 38 gigahertz. Then horizontal axis taken, I mean bending analysis along x-axis I taken into consideration, but there is no change in the higher band, but little change shift in the lower frequency band. Okay, but it is still less than minus 10 dB. Okay, at this point. And my gain, the gain of the antenna is increased from 5.6 dB to 9.3 dB. Okay, actually this is the antenna array for smartwatch application. Okay, millimeter wave antenna array for smartwatch application. So this is, you can see, this is the watch track. Okay, this is the skin, fat and muscle. Okay, I kept the antenna on these human tissues. Okay, and then I simulated and I got these results. Okay, this is still operating at 28 and 38 gigahertz. Okay, okay, this is the difference between the single element and the two elements antenna. Okay, the single element of size was this one. Okay, and the two elements antenna array of size this one. Okay, and the both are operating at 28 and 38 gigahertz. Okay, and the efficiency is this one. Okay, and the size is increased from this one. Okay, first with the single element the gain of the antenna is more than less than 6 dB. Okay, but in the case of the two elements antenna array it is more than 9 dB. Okay, so my gain of the antenna is increased. Okay, now I am going to make this antenna into 4 elements antenna array. Okay, and I compare the results, if I made the single element antenna, I compare the results with the previous research of the single element antenna, and when I converted the two elements antenna, then I can compare the results with the two elements antenna array of the previous research. Okay, now this is the chapter 4 of 4 elements microstrip patch antenna array. Okay, and you see I have converted the patch into 4 elements antenna array. Okay, this is the 4 elements antenna array. Okay, and it must be operate at 28 and 38 gigahertz. Okay, if it is not operating at 28 and 38 gigahertz, then you can say you did not use perfectly this matching stubs. Okay, so you need to vary the values. Okay, even if you use equations, you need to change the values little bit. Okay, you need to do optimization to check at which frequency bands my antenna is working. Okay, and you see that's one it is still 28 and 38 gigahertz. Okay, so it means the matching stubs are perfectly matched with each other. Okay, and also here the characteristics bandwidth is increased. Okay, and the gain of the antenna is increased more than 11 dB. Okay, and you see this is a direction addition pattern, okay, in the case of the 4 elements antenna array. And then you can see the surface current at 28 gigahertz, okay. You see also the matching stub has contribution in the frequency bands, okay. Okay, so this one is for the 38 gigahertz, okay, and you see these antenna elements are resonating, okay. And also, did you notice one more thing here in the 2 elements antenna array? I did not highlight here, but the change, I mean the spacing between the antenna elements, okay, here you also need to take into consideration these spacing, okay. In the case of the 4 elements antenna array, maybe they are more closer, okay.
Yes, they are very closer.
Yes, so you need to optimize these values, okay. And also I try to keep the size of the antenna compact, okay. If you notice the comparison table, I also added the you see banding analysis, okay. This is a I used the Roger 5880, okay, and you see the banding analysis taken into consideration, and you see this is operating at 28 and 38 gigahertz, and also along y-axis. This is on human tissues, okay. And this is the comparison table of the single element, 2 elements and 4 elements antenna, okay. And here the size of the single element antenna is 6 cross 5, okay, and here it is suppose 11 cross 9, okay, and here it is 12 cross 19.5, okay. And you see the difference in the gain, okay. Here in this case what is the gain, and here it is more than 9 dB in the 2 elements antenna array, and here it is more than 11 dB, okay. And also the size is still compact, not much more bigger, okay. And the efficiency in this case is more than 90%. If you mismatch the stubs, then you may reduce the efficiency, okay. So your perfect matching may increase the efficiency of the antenna, okay. And then the 4 elements antenna array are compared with the previous research of the 4 elements antenna array, okay. And you see the size is still smaller than the previous one, okay. And we have achieved the higher gain than the previous research. Did you understand the concept of the antenna array and how it works, and what about the gain and efficiency? Do you have any question?
For me, it's clear.
Okay, perfect. So let me share my some ideas regarding the antenna arrays, okay. Once we decide the topics, and surely we will work on it, and I will give you more ideas, okay, about the designing, because in 3 days we have to complete the work, design process, okay.
Yes, I think if we use the metamaterial, maybe you increase again more and more, yeah.
This is a good idea.
Yeah.
Yes, but one more thing, as I told you, suppose in antenna arrays, you suppose you have a substrate, okay, and in antenna arrays, if you do not use the full ground plane like this one, this suppose this is full ground plane, and you are using antenna array. In antenna array, if you use full ground plane, then you will get more higher gain, okay. But if you use CPW technique, then you cannot achieve more high gain, okay. So in the case of the metamaterial, I told you in the previous, maybe I will explain further. Yes, in the metamaterial you cannot use full ground plane, okay, because if you use full ground plane, then will be no effect in the of the metamaterial, okay, then metamaterial will be useless, okay. And then if you move towards the CPW fed antenna array, then you will only see the contribution of the metamaterial, but it will make our design not low profile, okay, it will make design very thick, okay. So we need to use foam and
For ground plane, you can use it as a superstrate.
For this one you can use partial ground plane like this one, as in the paper, okay, this one, okay. If you want to implement the metamaterial, then you can use partial ground plane, okay.
I mean, if in the case if you are not use CPW, you can use the metamaterial as superstrate.
Yes, superstate, for the superstate, it is still I am talking about the thickness, I mean the thickness. Suppose your antenna is here, suppose this is your antenna array, and surely metamaterial sometimes do not work very closer to the antenna, so you need to take some form of 5 millimeter, and then you need to place your metamaterial, and you see that it is will become thick profile, okay, so it cannot be called low profile.
Maybe we are afraid if you're using the metamaterial, maybe we'll have the same gain if you're using maybe the complete ground or the full ground.
But I suggest you to apply new technique, as this one has done this one, like this one. You can also try this one, okay. We can try this one, okay, to modify some shape, and to maybe we can do one more thing, I have one idea. Like we have a antenna here, this is a substrate, okay, and I am now talking about the front side of the antenna, okay. On the front side of the antenna, suppose we can use MIMO antenna with array, okay. This is the one field line, and this is another field line, okay. And then suppose this one is here and this one is here, okay, this field line, okay. And then we connect the shorting pin here, okay, at this point, okay. At this point we have, you connect the shorting pin, and then on the other side of the antenna we can make here a patch, okay, that works like this, okay. Okay, and here there is a patch, okay, that works like this, okay. And now the question arises about the ground plane, how we can connect the ground, okay. If we can even use CPW here, okay, very small size CPW here, okay. And also in one paper I noticed that let me show you one great idea. I in one paper I saw one most important thing. Let me create the other. There is a slow. I saw one paper, they did not use the ground plane in the MIMO antenna, but they even use, let me explain here. Suppose this is your substrate, okay, and how suppose you are using for cross form antenna, okay. Okay, this is for your first antenna, okay, and this is your second antenna. Okay, suppose this one, I think how they have connected, yes, I think they have used the 8 elements antenna on a very less size of the substrate, okay. Suppose this one, this is the front view, okay, this is the front view, okay. We know we have a port here, okay, and how they have connected the ground, okay. Actually they use the patch, full patch, okay, and they also use this radiator, this patch as a ground plane, okay. Like uh, suppose the ground plane of this antenna is the this patch, okay, this the second element, okay. How they have it, I forgot, I mean I lost the figure here. I downloaded the paper, but I forgot the, I also taken the picture, but I not here, it is not here, okay. But it was an amazing idea. Even they did not solder the connector with the patch, because if they solder, the results may change, okay. Let me think how they have done. Okay, suppose like this.
And where he put the port?
Let me explain. Yes, let me change its color. Suppose this is on the, okay, also let me change this color. Okay, suppose this is your ground plane, okay, and this is your let me shift to the back side, okay, back side. Okay, like this. Yes, this is your antenna, okay. uh, like this one is your antenna, first element antenna array, first element of the MIMO, and they have used port here, and they have used the backward antenna, this antenna, as a ground plane, okay, of this antenna. Did you understand what I mean?
And for the second antenna, how they connect?
They have used four elements antenna. Here I am talking about the two, but they have used four elements antenna, okay.
He repeats this shape again. Yeah, he consider maybe the two antennas, front and the back, maybe one item. Yes.
Yes.
And he repeats this shape again.
Yes, I forgot now, but I am just sharing the idea how they have used, this is the first antenna, and they have used the ground plane of this antenna, this one, this patch, okay.
But what about the result?
Yes,
The
results are.
I am down about the result. Yes.
I saw the results. Actually, they have submitted the paper in scientific report journal. Okay, because when you submit the paper in scientific report journal, they publish. Sometimes they publish as a on a research square. Okay, like preprint, as a preprint. Okay, so I studied the
Okay.
preprint of the paper. So I think, but I don't know either there was a four elements antenna, or I think either they are eight elements antenna, but I forgot. But there are antennas. I think they are four elements antenna, maybe eight elements. Sorry, like this one. You have antenna here. Let us try with the eight element. Okay, so we can, but it is not a very perfect idea. We go to connecting the port. Okay, this is your antenna 1, antenna 2, okay.
But in this case, is MIMO is not array.
Yes, I am talking about MIMO. I am not talking about array. But they have used, how they have used the eight elements antenna. Actually, it was the eight element antenna. Okay. I forgot how. I think. I think this like this. Not like this. Not. I forgot how they have used 8 elements and how they have used the technique, because the ground plane of the first antenna is the of the second. I mean they have used like this antenna as the ground plane of the other antenna, and this antenna used as the ground plane of the this one antenna. Okay, like this.
So is that like a reference, the second antenna in the ground plane?
Yes, actually there it was a 4 port but 8 elements. 4 ports but 8 elements, my
I
antenna.
mean, the second patch in the ground is a reference for the positions of the patches.
The same position as this 4 one, okay, but I don't know how, how they have in how position they have used. I forgot, because that was a really good idea. I forgot
It's
now.
crazy idea.
Yes, I was thinking about that. I forgot now, but that was the amazing idea. How they have connected the 4 port but 8 elements my antenna. Even the size of the antenna still remains same. If you connect this design here, you cannot connect the port here, okay, of this design. Okay, let's try with the 2 one. Okay.
I try to imagine it, but I can't.
Yes, it is. I think it is like this. Yes, in this way. Okay. Yes, like this. Yes, like this.
Great. But the most important is the diversity.
This one. This one is okay, but this one I don't know how, or maybe like this. But I just imagine that all the antennas are orthogonal to each other. Okay. Because this antenna is you see here, you are not able to connect the port here of this antenna. In this way you can say. Yeah, I have four. This is you see how many ports, yes, 4 ports and 4 elements antenna. Okay, quad port MIMO antenna. Like this one. There are a lot of ideas. I told you, if you apply a new technique, new idea, then maybe you will get target high quality journal. Okay. So antenna arrays, if very less researchers have used shorting pins. Okay. You can use shorting pins, and also in antenna arrays you can use what I mean you can make it circularly polarized. Okay. In antenna array, very less designs are circularly polarized. Okay. I will share the papers, okay, by email. Don't worry about the matching stuffs. So do you want to share any other thing? Yes.
Also, the paper of DRA also, I think we don't share it. Please, if it is possible. Yeah.
Okay, I will share again.
If you have time, we can share it. DRA. Yeah.
Bro, Sarush, also the MATLAB code, if you remember.
Yes, yes, I remember. Sometimes I because I have long time classes on the working days. Okay, I came late at night at 8 p.m. Okay.
Also, if you have some information, give me some information about the Spark 3D. There is conjugated with the CST program 2021. I don't know how to use it.
Which one you are talking about?
I want to talk about the conjugated program or with the CST Spark 3D. I don't know which is.
I don't know if you can show me the paper or the screen, or I mean the photos. Maybe I can understand. Okay. In the reconfigurable antenna, we will study this portion. Okay, schematic portion. This is a very interesting portion. Okay, and we will study about it. Okay. In the reconfigurable antenna, we will discuss more ideas. Okay, maybe we will touch some other fields. Okay, like sensors and filters. Okay, we will learn how there are many ways to make a reconfigurable antenna. Okay, there are I think 3 to 4 methods to design a reconfigurable antenna. One is this one. Okay, and the three are in this portion. Okay.
Could you give me more information about schematic in the next lectures or workshop?
In the reconfigurable, we will study. I mean, I am just telling you about this one that we will study in the next lecture. In this lecture, reconfigurable. Okay. In the reconfigurable, we will study this portion. Okay.
Okay. Mr. Sarge, for the next lecture tomorrow,
Yes.
we talk about millimeter wave.
Yes, I also touch terahertz antennas because some people are asking me.
What frequency you choose? You want to?
For the millimeter wave,
60 gigahertz?
what?
At 60 gigahertz.
In my one paper, I use 60 gigahertz. This one, okay. This is 28, 38, and 60 gigahertz. Okay, because these are millimeter wave bands. Okay, greater than 28 dB. Okay, gigahertz. I use the most important millimeter wave band is 28, 38, and 60 gigahertz. Okay, this design is tri band.
Because I work at 60 gigahertz
Mm-hmm.
and I use the metamaterials substrate.
Mm-hmm.
There are rejected.
Yes, you sent me one paper.
Yes.
Do you remember? You
Yes.
sent me the paper. This because that one I think without fabrication and measurements, right?
Without fabrication, yes.
That's why. Okay, these are papers on my antenna
I
arrays.
sent it to the conference.
What?
I tried to maybe it's accepted.
You can if you are not able to make a design. I mean, not fabricate. Then if they are rejected continuously, then you can submit in a book chapter. Okay, you can publish book chapter on them.
Okay. Can you tell me how?
Actually, book chapters are not like a journals that you submit on the website. Actually, there is a call just like a conference paper. Okay, like a conference. You hear a call from the like. Let me show you here. There is a book chapter call.
I got it. I understand you now. Okay.
Yes, there is a poster like this. Okay, whenever you see like this one, call for book chapters. Okay, sometimes if they are offering like for a Springer. Okay, maybe there is a book chapter of Springer here, not here. Here is this one. Okay, sometimes they call like this. It does not take much time. Like this one, you can see here. These are the dates. And in the book chapter, the acceptance rate is good in Springer. Okay.
How to get this?
Actually, I have links with many professors. They send me these things. Okay. They send me many times. Okay, like for this one I submitted recently one paper on terahertz. I show you one paper. Okay, uh, not this one. This the professor one professor sent me the poster, and I submitted the paper with this poster. This
Without
is
fabrication.
yes, without, because these are terahertz. Okay, so in these are, this is covering terahertz antennas. Okay, and you can
Is there
also I
is
think the
there a fees
no any
for this?
fees, no any fee for the book chapters.
Okay, good.
They have written this one. Okay, you can see there will be no publication charges, and
And not
acceptance
the
rate is good.
Springer.
Yes, and then it will publish in a Springer book. Okay,
That's good.
yes, you can see here, you will find option here Springer. Okay, and your book will be published in a Springer. Okay,
That's good.
so in this way you can try this one. Okay, this professor told me they will send me another poster. This is the first, and I submitted two chapter in the previous poster, and now they are published. Okay, on the website. Okay,
Okay, thank you.
yes, when they send me I will send you. Okay, they told me this poster is for the terahertz, but they will also launch another poster for the sub 6 gigahertz frequency bands. Okay, and then we can target book chapter. Okay, I will share with you.
Thank you.
For the DRA I am sharing. Okay, we,
Mr. Sarosh, I
yes,
want to ask you how the upload you have.
what,
I mean the upload.
this one, or you are talking about the
The
video?
speed, the speed of your internet. I
uh,
see it's very speed, speed fast.
yes, because I am not in Pakistan. In Pakistan or in
Because
other
because
countries it is very slow speed, but here it is very, I think,
because
5 MB per second.
for the for the same size in my country, it's take 1 day for upload.
And that's why you see you get very easy, very urgent notification of the videos of even they are very more than, I don't know what is the size. Let me check the size of the videos. Suppose this one, the size of this video is 2.46 GB. Okay,
Wow,
and they upload in
and you
less than
upload
30 minutes,
non-stop.
and in
Yes,
20 minutes they upload the video.
that is good internet.
This is I am now at home. Okay, and this is the internet at home. In the university it is more faster than this one.
Oh, that's amazing.
Okay, what are the other things you are asking to share? In which lecture we did study implantable antenna? There is lecture 10. Lecture 10. Lecture 10. Okay, I save this one as a picture and I will send you. Okay, once we start the writing part of the papers, then I will provide you and more information. Maybe someone like to work on my antenna, and in the videos maybe they did not find much knowledge, and once we start and we will write in the paper. Okay, and we will add whatever we need. Okay. these days I am working on reconfigurable antennas, and you will see, I hope inshallah in few days you will see my another paper in IEEE. Today I received the yesterday I received the reviews of the IEEE paper. There are some reviews, but not much, only 3 comments, and only 2 comments here, and just 2 comments here. I hope it will be accepted inshallah.
Inshallah. Inshallah.
And don't worry, once we start, then you will see you will publish very good quality journals.
The hard step is the first step.
What?
I mean,
Yes, the first step is the hard. Yes. And you see, my first paper I wrote in more than 6 months, and my first paper was in IEEE, and I learned a lot with my first paper.
You know, Brother Sarush, my first paper, it was in Taylor and Francis. You know, Journal of Electromagnetic Wave and Applications. I get used to publish in it. You know this Journal of Electromagnetic Waves and Applications in Taylor and Francis, yeah.
Yes, I know. I think it is now Q2 or Q3. I forgot now.
I think Q2 now, yeah.
Yes.
But I think now is not accept band antennas.
What this Journal of Electromagnetic Waves and Application?
Yes, but I think now is accept